Friends, we shall discuss today three important aspects of stability analysis. One is the tangent stability, voltage stability, and long term and mid term stability. All these topics will be covered in detail in subsequent lectures. Today I will simply give you the basic concepts related to these three stability problems. First we consider the tangent stability. As I told you earlier that originally the tangent stability was the only stability which was of concern and which was analyzed in detail. The tangent stability is the ability of the power system to maintain synchronism when subjected to severe transient disturbances. Let me emphasize here that tangent stability is the ability of the power system to maintain synchronism subjected to severe transient disturbances. The word severe transient disturbances to be carefully understood. The disturbances occur suddenly. They are severe in nature. Now, the examples of the disturbances are transmission line faults, sudden large load changes, loss of generating units, and line tripping. Now, these are the examples which can be considered, which are considered for studying the behavior of the system. Now, some of the important features we have to understand about the tangent stability are: the resulting system response involves large excursions of rotor angles and is influenced by non-linear power angle relationship. Now, here I am again trying to emphasize that whenever large disturbances occur, then the resulting response involves large excursion of rotor angles. The delta varies over a wide range, and therefore, the power output is highly nonlinear with respect to delta. This is one important aspect, and therefore, tangent stability analysis requires the solution of nonlinear swing equations. The stability depends on both initial operating state of the system and the severity of the disturbance. That is, for each operating condition, the behavior of the system is going to be different. Similarly, the severity of the disturbance. Now, severity can be depends upon the type of fault, location of fault, and duration of fault. Similarly, when we talk about the large load change, what is the quantum of load which has come on the system? Similarly, when we talk about the generator dropping, what is the amount of generation that has been taken out from the system? And therefore, these two important points we have to carefully understand are that it depends upon the initial operating condition and severity of the disturbance. Usually, the system is altered so that the post disturbance steady state operation differs from that prior to the disturbance. Here, suppose the system is initially operating in a one steady state condition. The moment disturbance occurs, there will be change in the topology of the system, and therefore, if the system is stable, the new steady state operating condition will be different from the previous one. The disturbances of usually varying degrees of severity and probability of occurrence can take place in the system. Now, when we talk about a practical system, the disturbances which occur have different degrees of severity and different probability of occurrence. When we talk in terms of what we mean by the probability of occurrence, in any power system, faults occur in the system, but the probability of occurrence of line to ground fault is the maximum and the probability of occurrence of three-phase fault is minimum, right? And therefore, one has to look into this aspect while analyzing the transient stability of the system and also while designing the system for operation and planning. The system is designed and operated so as to be stable for a set of contingencies. For example, single phase to ground fault, phase ground fault, or three-phase fault. Now, here when we talk about the contingencies, we have to contingencies stand for these all abnormal conditions. Okay? And whenever we design the system, we have to see that what are the most probable contingencies, and the system should withstand those contingencies and it should not lose synchronism when such contingencies occur. Now, when we analyze the transient stability of the system, usually we assume the faults occurring on the transmission line. Sometimes we consider the faults at the buses or on the transformers. In any system, when the faults occur, the faulty system or faulty element is disconnected by the operation of protection system and circuit breakers. Therefore, we have to be very careful when we consider the analysis of transient stability, the operation of circuit breakers and protective relays. In some cases, we consider the high speed reclosure also. That is, circuit breakers have the capability to reclose after some time delay. Now, this reclosure may be a successful reclosure or it may be unsuccessful reclosure. In case the fault is transitory in nature and it clears by itself, then when you reclose the circuit, you will regain the original operating condition. However, if suppose there is a permanent fault, right, then the reclosure is going to be unsuccessful. We will study the effect of auto reclosure on the transient stability in our later lectures. With these basic points related to the transient stability, I will just show you a typical response of delta as a function of time for a given disturbance. This figure shows the behavior of a synchronous machine under stable and unstable operating conditions. Now, I have shown in this diagram three cases, case 1, case 2 and case 3. Case 1 shows that following the disturbance, the power angle increases, attains maximum value, then further decreases and oscillates with decreasing amplitude. This is a stable case. Case 2 is one where the response is shown in curve 2. In this case, the delta increases continuously till system becomes unstable or till machines lose synchronism. This type of instability is generally called first swing instability. And this happens particularly due to insufficient synchronizing power. The third case is a case where the power angle delta increases, attains maximum, but subsequently the oscillations grow in magnitude. This is a case where system is stable from the point of view of first swing stability, but the system is becoming unstable due to lack of damping torque. That is, the new operating condition is not small signal stable. Now, these curves can be plotted for any operating condition, for any given severity or given disturbance, and then we can examine whether the system is stable or not by examining the swing curves. They are all swing curves. These swing curves are obtained by solving swing equation of the system. The method of solving the swing equations we will learn subsequently. Okay. We shall be devoting a significant amount of time for analyzing the tangent stability of a system in our subsequent lectures. Now we address the problem of voltage stability. The voltage stability has become the subject of studies during the last 1 decade. Now, voltage stability is the ability of a power system to maintain steady state voltages at all buses in the system under normal operating conditions and after being subjected to a disturbance. You have to very carefully understand the definition. That is, again it is the ability, stability is the ability of the system such that it maintains steady state voltage at all the buses under normal operating condition and also after disturbance. Now, here we will see that actually when we talk about normal operating voltages, that means that the acceptable voltage profile of the system. Sometimes the voltages become very low, will not be acceptable, we call this as unstable system. A system enters a state of voltage instability when the disturbance, increase in load demand or change in system condition causes a progressive and uncontrollable drop in voltage. Now, here we are emphasizing the occurrence of voltage instability. That is, whenever a disturbance occurs, the voltage drops and it is not controllable, because any system we have certain controllers which control the system voltage, but disturbance may be of such a nature so that the controllers are not in a position to control the system voltage, and that is the condition for voltage instability. The main factor causing instability is the inability of the power system to meet the demand of reactive power. When we talk about the angle stability, it is a balance between active power, that is the mechanical input of the turbine or mechanical input from the turbine must be equal to electrical output from the generator. It is a real power balance. Here in voltage stability, we require the balance between the reactive power, that is reactive power generated and the reactive power consumed in the system. Then if in case the system is unable to maintain this balance, then the problem of voltage instability occurs. The heart of the problem is usually the voltage drop that occurs when active power and reactive power flow through inductive reactances associated with the transmission network. When you again look, what are the main causes of voltage drop? The voltage drop takes place in transmission system, in transformers or any part of the system due to the flow of real and reactive power, and the system has its impedance, resistance and reactance, and because of this there is a voltage drop in the system, and this drop is the primary cause of voltage instability. We shall be studying this voltage stability problem in detail in our later or subsequent lectures. However, I will just give you one basic ideas that the criteria of voltage stability. When do we say that system is voltage stable or system is voltage unstable? A simple criteria for voltage stability is that a given operating condition, for every bus in the system, the bus voltage magnitude increases as the reactive power injection at the same bus is increased. This point is very important. Suppose you have a large system, you have number of buses. Okay, if we inject reactive power at a particular bus, then the voltage of that bus should increase. If the operating condition is such that by injecting voltage at any of the buses, just correct me, by injecting reactive power at any of the system buses, the voltage should increase. There should be no case where I inject the reactive power and the voltage decreases. This concept can be further stated in the form: when we talk about voltage stable to say voltage unstable. A system is voltage unstable if for at least one bus in the system the bus voltage magnitude V decreases as the reactive power injection Q at the same bus is increased. Because when I talked about the voltage stability, the condition posed was that at all buses the voltage should increase when reactive power is injected. If at any one of the buses the situation is different, that is, when you inject reactive power the voltage decreases, right. That if at any one of the buses this happens, the system is voltage unstable or voltage unstable. Another way of stating this problem is, a system is voltage stable if VQ sensitivity is positive for every bus and voltage unstable if VQ sensitivity is negative for at least one bus. It may be more than one bus, okay? But if at any one bus the voltage sensitivity becomes VQ sensitivity, because not voltage, VQ sensitivity. That is change in voltage divided by change in reactive power injected. If you find this ratio, right, this is called the voltage VQ in sensitivity. And if the VQ sensitivity becomes negative at any one of the buses, we say the system is voltage unstable. Voltage instability is essentially a local phenomena. However, its consequences may have widespread impact. Another next point which I wanted to mention is the concept of voltage collapse. Sometimes we say that voltage collapse had taken place in the system. Now, this voltage collapse is a very complex phenomena which occurs due to occurrence of a sequence of events. But whenever the system voltage becomes unacceptable, if the system voltage profile becomes unacceptable to us, we say that voltage collapse has taken place. Okay. For analyzing the voltage stability problem, it is divided again into two categories. One is called large disturbance voltage stability and another is called small disturbance voltage stability. Just like as we had in the angle stability, we divided this problem into two categories: small signal stability and tangent stability. Tangent stability is particularly related to large disturbance. It is a large disturbance stability, right? So, the power system stability was classified as angle stability and voltage stability. We have studied basic concepts of angle stability. Now, we should study the basic concepts of voltage stability. The voltage stability is also classified like angle stability into two categories: a large disturbance voltage stability and small disturbance voltage stability. This voltage stability phenomena has been studied during the last one decade in depth. A lot of research work has also been done in the area of voltage stability. We will just study today the basic definitions of large disturbance voltage stability and small disturbance voltage stability and the factors which determine these two stability problems. The large disturbance voltage stability is concerned with system's ability to control voltages following large disturbances such as system faults, loss of generation and circuit contingencies. Here I emphasize that system's ability to control voltages. Now, in any power system, the power system voltage is controlled by controlling the controllable devices. The controllable devices are the automatic voltage regulators on the synchronous machine. We have online tape changers on the transformers. We have capacitors, shunt reactors. Then other devices are static wire systems, and these devices, when they are controlled to maintain the voltage on the system, and if the system can control the voltage following the disturbance, then such a system is said to be voltage stable. The voltage stability is determined by system load characteristics and the interaction of both discrete and continuous controls and protections. When we talk about the system load characteristics, we have to understand very carefully that the power consumed by load depends upon the magnitude of the voltage and frequency. There are some loads whose power consumed depends upon the voltage only. There are some loads whose power consumed depends upon voltage and frequency both. An example is a heating load, where the power consumed is directly proportional to voltage square. However, it does not depend upon the system frequency. But if I consider the induction motor load, then the power consumed depends upon voltage and frequency both. And therefore, when we talk about the power system stability, then the power system voltage stability, that is primarily determined by the load characteristic and the interaction of both discrete and continuous control protections. When I talk of discrete controls, these are the on-off controls, and continuous controls, the example is automatic voltage regulators. Similarly, the static wire systems are continuous controls. The criteria for large disturbance voltage stability is that following a given disturbance and following system control actions, the voltages at all buses reach acceptable limits. In any system, we can operate the system in case the voltages are within certain acceptable limits. In case the voltage can be controlled within the acceptable limit, the system is said to be stable. Now, we discuss the small disturbance voltage stability. Small signal voltage stability is concerned with the system's ability to control voltages following small perturbations, such as incremental changes in system load. When we talked about the large disturbance voltage stability, the disturbances were large in magnitude, while here when we talk about the small disturbance voltage stability, the disturbances are small in magnitude. The example of small disturbance is the incremental changes in system load. A criteria for small signal disturbance voltage stability is that for a given operating condition, a system is voltage stable if VQ sensitivity is positive for every bus and unstable if VQ sensitivity is negative for at least one bus. I will again repeat here the meaning of VQ sensitivity. That is, at any bus, if I inject a reactive power, then the change in voltage divided by change in reactive power injected, this gives the VQ sensitivity. And for the system to be stable, at all buses in the system, VQ sensitivity should be positive. And if VQ sensitivity is negative at any one of the buses, system is said to be unstable, voltage unstable. The voltage instability does not always occur in pure form. Often the angle and voltage stability go hand in hand. Here I want to emphasize that system is 1, and whenever disturbances occur, it affects the system angle as well as the voltage, and therefore, both these phenomena go together, and whenever we analyze the total system stability, one has to take care of both the aspects. We shall study the voltage stability phenomena in detail in subsequent lectures. Now, we will define another very important term known as the long term and mid term stability. This is also a new phenomena. Earlier, the designers and operators of power system did not consider this problem. This long term and mid term stability have been introduced as a result of the need to deal with problems associated with the dynamic response of the power system to severe upsets. The severe upsets are those disturbances that result in excursions of frequency and voltage and power flows either so great or so long lasting that they invoke the actions of slow processes, protection systems, and controls which are not modeled in the conventional transient stability analysis. Because when we analyze the transient stability problem, we do make certain assumptions, but however, in long term and mid term stability problem, the disturbances are so severe in nature, so it results into severe upsets in the system. The frequency and voltages fluctuate over a wide range, and this will invoke the action of certain controls which otherwise were not modeled. Long term stability analysis assumes that inter-machine synchronizing power oscillations have damped out, and the result being uniform frequency. Now, here I want to emphasize that whenever a disturbance occurs, system is in dynamic condition, but the moment sufficient time has elapsed, then the system will settle to a low frequency, low voltage, and frequency can be assumed to be uniform all through the system. The focus is now on the slower and longer duration phenomena that accompany large scale upsets and on the resulting large sustained mismatches between generation and consumption of active and reactive power. These phenomena include boiler dynamics of thermal units, penstock and conduit dynamics of hydro units, automatic generation control, power plant and transmission system protection and controls, transformer saturation, and off nominal frequency effect of loads and the network. This I will just discuss this thing one by one. When we talked about the tangent stability analysis, we have assumed that mechanical power remains constant. We did not model the boiler dynamics, turbine dynamics. For hydro turbines, we did not model the penstock and conduit dynamics. We also do not model the automatic generation control, which is a secondary control to regulate the real power output of the generators. We have also not modeled the protection system in the transmission, transformer saturation, and the effect of off nominal frequency effect on loads and network. Now, here when the system voltage and frequency deviate widely from the nominal value, the transformer core may get saturated and it has effect on the system performance. Similarly, when the voltage and frequency are low, all these controls get activated or invoked. Similarly, when frequency is quite away from the nominal, voltage is away from the nominal, it affects the system load. And therefore, when we analyze the long term stability, these phenomena need to be modeled and dynamics need to be analyzed considering the detailed models of these devices. The next point is about the mid-term stability. The mid-term stability is between the tangent stability and long-term stability. Now, we can say that mid-term response represents the transmission between short-term and long-term responses. That is basically transition between short-term and long-term responses. In mid-term stability studies, the focus is on synchronizing power oscillations between the machines, including the effect of slower phenomena and possible large voltage and frequency excursions. As I mentioned that when we talk about the long term stability, we do not consider the synchronizing power oscillations, while in mid term we consider the synchronizing power oscillations. Now, severe system upsets result in large excursions of voltage, frequency and power flows that thereby invoke the actions of processes, controls and portions not modeled in the tangent stability studies. The typical ranges of time responses. The tangent stability is studied over a period of 0 to 10 seconds. Generally, it is over a period of 0 to 3 to 5 seconds. Only in those cases where we have a large system and there are inter-area modes of low frequency exists. In those cases, the time period of oscillations may be large and therefore, the tangent stability is analyzed approximately in this range of 0 to 10 seconds. It is not a very rigid boundary between the tangent stability, mid-term and long-term stability. Now, mid-term stability is from 10 seconds to few minutes, while long-term stability is from few minutes to tens of minutes. Now, with this I will conclude that today we have addressed tangent stability problem, voltage stability problem and mid-term and long-term stability problems. We have seen actually that the tangent stability is the ability of the system to maintain synchronism following large disturbances. It depends upon the system operating condition, severity of the disturbance. Similarly, the small disturbance stability which we studied earlier also depends upon the operating condition of the system and type of disturbance. The voltage stability, we have addressed the basic concepts related to large disturbance voltage stability and small disturbance voltage stability. We have seen actually the primary criteria for analyzing the voltage stability of the system. While talking about mid-term and long-term stability, which are new in the area of power systems, we have seen actually that whenever there are severe upsets in the system, one has to model the dynamics of slow processes, controls and the effect of frequency and voltage excursions on the system loads. With this, when one is in a position to analyze the behavior over a long duration. Further, I would like to emphasize that these three stability problems, mid-term stability, mid-term and long-term stability, tangent stability and voltage stability, they are interrelated. The modeling is similar in nature. With this, I conclude my today's presentation. Thank you.